Hi, everyone. Thanks for bearing with those technical difficulties, but we're ready to start. So first today we have Sarah Shamek. Sarah is an assistant professor of atmosphere and ocean science and mathematics at the Courant Institute of Mathematical Sciences at NYU. She studies atmospheric processes using machine learning.
Thank you for the introduction, and I'm happy to be here and talk about some of the work that I've been doing over last semester. So I'm going to talk about modeling rain and modeling rain area as a source of predictability if we want to represent rain. This is a collaboration with Pedro. Pedro is a PhD student at University of Washington, and he was very generous to provide his data. So that made this study possible. So let's start with a little bit of motivation. So precipitation still seems to be one of the most challenging parameters or variables to predict in climate and weather models. Here I'm showing two plots to confirm that argument. So the one on the left, it's to your left as well, right? Yeah, the one on the left shows daily rain from three sources. CAM is community atmospheric model. SPCAM is community atmospheric model, but within each grid, you have a 2D representation of a smaller scale. And then CPC is observational precipitation. The point of this plot is that the tail of distribution is kind of missing, and you don't reconstruct the same distribution that you observe in observation in the models. Specifically, when you go to let's say 3-hourly precipitation, the mismatch between the distribution increases largely. And the one on the right shows Arrow 5 precipitation and TRIM. So TRIM stands for Tropical Rainfall Measuring Mission. It's a satellite going over the Earth that scans the clouds and it measures the rain at the surface through the radar reflectivity. So the two on the bottom shows latitude versus time. So you can see how a convective system propagates from, let's say, equator toward 10 degree of north. And then for two different seasons. The one on the top shows Arrow 5 representation of the same system. Arrow 5 is reanalysis data. It combines the model output and observation to produce a seamless reproduction of the different variables. And you see that the propagation is very badly modeled by Arrow 5. And also the amount of rain, the strength of rain is also kind of largely different from the one that we observe in observation. So now I'm going to talk about a little bit about the convective systems and they being important source of rain, specifically when we talk about the tropics. So the image that I'm showing here is a very nice image of convective system. I hope that you see many of them. And it has different components. So this upper part is called ambient cloud, and then you see this core here that is strongly raining, and then the tiny little cloud that is start forming at the edge of this convective system. On the right, I'm showing a very cartoonic representation of this system, and also you have the time component. So the first column shows the top view from the system, and then the second column shows the vertical cross section. If you look at this vertical cross section, this first one, you see that at the beginning you have a strong updraft that transport a mass of water vapor above, a mass of water vapor upward, and that rains down. So this is, let's call this a convective core. And then later on, that convective core kind of stop stop being connected to the surface. And it's sort of like the rain weakens, but the rain area increases. So that region here, let's call that the stratiform. And then you see that the new convective area start to appear at the edge of the system. So the nice thing is that these two categories of rain can be easily detected from the radar based on the reflectivity that the radar measures when they send out the radiation, and the radiation will be reflected back, and the radar can measure that. They can categorize that to the different type of clouds that are the source of rain. So here we have convective cloud, and then on the left you see the stratiform component of it. So all of this being said, rain amount has a large dependency on the humidity that you have available in your in your atmosphere. So if you have more water vapor, you could rain more. But more importantly, there is this large increase of rain with the humidity that is available, but that seems to be very much related to the amount of like the rain area that you have available. So the main contributor to increasing the rain is not the intensity, it's the rain area. And the question that I want to ask is first, can we verify this argument that rain area is an important source of predicting rain amount? And if yes, then can we build a model to predict rain area itself? So here is to quantify, to answer the first question, if rain area is an important source of predictability. So you see a lot of dots here. First thing to notice is the colors. Those are showing the different regions over the tropics. I have South America, African continent, Central Indian Ocean, and Whirlpool, that's over Pacific. And I'm predicting for each region, combining some larger scale data that I'm going to define. And in one of the group on the left, I'm not showing my models, what is the rain area. On the right, I'm showing what is the rain area. You also see two different symbols. One is this circle, so that is the total rain that I get from stratiform and convective. And the other one shows the rain only from the convective component of the system. And we see that when we have the rain area available, so these dots here, we can predict the rain much more accurately compared to when we don't have that information available. And I also divided my data to like include all of the data point that I have, and also to only include extreme rains that I define as the higher percentile of rain. So this verifies that, okay, maybe precipitation area is a good source of information if we want to predict rain. Any question? Yep.
Where is this data coming from?
I'm going to talk about that. Yeah. This is a kind of like a reconstructed a talk, so it's kind of like the order is not that nice, but please ask if you have any questions. Okay, so where the data comes from. Let's say I have the satellite that moves around the Earth, and on its way, it's going to scan the clouds. Here I'm showing a 2 × 2 degree image that I took from this path of my satellite. And the data can be categorized to stratiform and convective rain within that cell. And here I colored them with red, that is the convective component, and the green, that is the stratiform. And if I plot them in a plot that has free tropospheric precipitable water and the x-axis and the percentage of my grid that is covered by those two clouds, I get these 2 points, right? So 30% of my domain has convective rain, and about 40% has a stratiform rain. Precipitable water is the integrated amount of water vapor that we have in the atmosphere. So now this is only one trajectory and one 2 × 2 degree grid. If I take all trajectories and many of these 2 × 2 degree grids, I get a plot like this one here. So I'm showing again the rain area for both the stratiform and convective versus free tropospheric water vapor. The orange or reddish color is the convective one, and the green one is the stratiform. And the question that I want to ask is, what environmental variable controls these two fractional area? And can we actually write down an equation for them or develop a model that tells us what is the amount of rain that I'm supposed, what is the coverage of rain that I'm supposed to get? The challenge that you can already see is that in this process seems to be very stochastic. That means that for a given large scale condition, you may get really different combination of these two variables, like a large variability on how large is the coverage of your rain area. So the process is stochastic, and we need to think of a way to model that. Another detail that I have to tell you here is that here I picked free tropospheric water vapor as my independent variable, or as my x-axis, but there isn't really any argument to, well, there isn't maybe like a very strong reason to pick that one versus different variable that I could choose. I'm going to get back to that a little bit more. So I prepared this slide for audience that they don't do machine learning. So if you see it's too basic, it's because I kept it the same way, but I'm gonna try to add more details. So usually what people do, they pick one variable that they think is mostly related to the rain area or to the rain itself, and then they bin the data over that specific variable. Here, that variable being precipitable water. They average over bins, and they talk about the average over those specific bins. I don't like this method because that kind of bring in what variable I choose to build my bins. Maybe it's not the best variable. What if I have like multiple variables that are to some extent correlated? Which of them I should pick? So here, what I wanted to emphasize is that for each of these little bins, I can have a distribution. Let's call that my conditional distribution. That each of these bins have their own distribution with, let's say, mu, sigma, and that little alpha. So the mean of distribution, it's variance, as well as this alpha, that is the ratio of the two categories. And those parameters changes depending on where I am in this bin. So what if we reconstruct this whole distribution and then somehow explain those parameter of the distribution? So I'm going to try to do this. I'm going to try to reconstruct the whole distribution, but instead of picking only one larger scale environmental variable as my explaining or my independent variable, I'm going to pick a range of variables that I'm going to talk about. I'm going to reconstruct the distribution, and then I'm going to measure or compute these parameters. So I'm going to combine then a generative machine learning that's going to do this for me. And then once I have those distribution, I'm going to use equation discovery to connect the larger scale environmental conditions to those parameters. So the data that I have, the stratiform and convective rain area comes from precipitation radar. I'm looking only over the tropics, so 20 south to 20 north, and I'm picking 4 different regions, 2 oceans, and 2 land. And then for my environmental condition that I'm going to show them, I'm going to refer to them as X of larger scale. I'm using Aero 5 data. Everything is regridded to 2 in 2 degree. So that another complication is that the stream precipitation radar data can be considered as instantaneous. The satellite passes and it scans only once, while the Aero 5 is hourly average data. So there is a mismatch between the two. But unfortunately, that's the best that we can get. One thing that is a little bit heartwarming is that larger scale environmental variable, when it's averaged over a degree of, or a domain of 2 in 2 degrees, not going to have a large variability. Okay, so from the Aero 5, I'm going to take the whole column of the atmosphere and I'm going to split it to 2 parts, the boundary layer and the free troposphere, because that's going to reduce the amount of information that I have, and it makes it easier to interpret what my model learned. If I include the whole column, I'm going to get probably a more accurate model, but it's going to be more difficult to argue what the model is actually learning. So this image is actually funny because the boundary layer is about like a kilometer, but this guy is feeding in the boundary layer. So this guy is a giant guy. And so my boundary layer goes from the surface to about a kilometer, and my free troposphere goes from 1.5 kilometers up to 4 or 5 kilometers above the surface. And I'm picking variables that previous papers refer to them as being important for precipitation. That includes precipitable water, or this integrated amount of water in the atmosphere, relative humidity, temperature. So those so precipitable water, relative humidity, temperature, and potential temperature, they give me the thermodynamics. I have vertical velocity, or omega, measured in pressure level, as my dynamics, and CAPE also as a dynamic. There are some argument around should we use omega or not. We can talk about that. And yeah, so I'm going to refer to my variables as free troposphere versus boundary layer. Again, a very simplified slide for a non-machine learning audience. I'm using a variational autoencoder. I have also used the diffusion model. The variational autoencoder seems to be doing better, maybe because I only spent 3 hours on the diffusion model, didn't try to like tune it better. So the way that I'm training this is to pass the pair of a stratiform and convective, condition that on the larger scale, and then in this component that I'm showing, I'm only showing the decoder component. So the noise is then, again, conditioned on the larger scale. And once I sample one noise, that's going to give me a pair of a stratiform and convective rain. So now if I pass many noise conditioned on my larger scale, that's going to give me this conditional distribution then I can measure the variables, the statistics of that distribution. And if I iterate over all of the larger scale variables that I have, I can reconstruct this whole joint distribution of my stratiform and convective rain. Okay, so let's look at some slides. Some results. So here I'm showing on the left what my model predicts. I have the percentage of the domain covered by convective area versus the same for stratiform. And on the right, I'm showing, on the left, I'm showing the predicted one, and on the right, I'm showing the observed one. It's difficult to have a one-to-one comparison between these data, so I have to somehow compare the distribution. Visually, the two looks pretty similar. If I measure the distance between the two distribution using KL divergence, that's also somehow close. It's about 0.1. So that's heartwarming. It tells us that maybe our model is capturing something meaningful. I can do more tests. So I'm looking at the mean of each of the distribution that I have. So this is for each larger scale condition, what is the expected amount of rain for each of the categories that I have. So that's going to be this distribution here. I don't have that from observation to compare for, but I can feed a linear regression line to that. That's going to give me a slope of 0.14. So that tells me that about 14% of the stratiform area is going to be convective area. And that value compares pretty well with the previous studies that argued that, or like use observation over a longer period to argue that that value is about 80%, 18%, or 15%, depending on the studies, but they use a different source of data. So I don't expect the two to have a one-to-one matching. So this linear regression told me what is the ratio of convective to stratiform on average, but also, I could also look at that for each of the conditional distribution to see if that has a variability with the larger scale condition. And we see that that could change from 0 to 30% or even much more than 30% because I cap this. I have conditions that I have a stratiform but not convective. In that case, if I fit a linear regression, the slope of that is going to go to infinite. So I cap this to 0.30. So this shows that, well, when we have the beginning or when we are at the beginning of our convective system, we don't yet have the stratiform component. So the slope becomes much larger. And then little by little, when we evolve within the life cycle of the convective system, the stratiform component becomes larger. So the slope reduces. Okay, so my the question that I was very interested in when I started this is what environmental condition actually controls this rain area. I'm going to answer that, but I want to also emphasize that this is going to be an association or a correlation between the two happening together. It doesn't yet have any causal direction telling me that this variable is going to result in the other one. It's just a correlation between the two. But it's nice to see that the mean value of my convective. So the way that I'm doing this is now I'm computing those means from my conditional distributions, and then I'm using equation discovery to connect my larger scale to those means and standard deviations. And it's doing pretty good. So the R squared for the convective component is about 0.8, and the R squared for the stratiform component is about 0.9, or it gets to 0.994 as well. And then the variables that contribute largely to convective is velocity weighted free tropospheric moisture plus boundary layer moisture. And for the stratiform, it's again velocity weighted free tropospheric moisture, but now free tropospheric moisture has this power of 3, which is very large. And then for the for my variance, the model again picks PW, but it's interesting because it adds up the boundary layer water vapor to the free tropospheric one, which means that probably it's trying to like figure out the whole column water vapor matters for this variable. And then it adds some contribution from the temperature, from the free tropospheric temperature. So in a sense that if you have a colder free tropospheric temperature, it seems to be favoring the spread of that rain area. And then again, for the stratiform, the model picks the power 3 of column water vapor, which is still to me a mystery to physically explain why we get power 3 of water vapor. Okay, I can wrap that up. I try to reconstruct the joint distribution of my rain area. I condition them on larger scale, and then I can basically compute the statistics of the distributions that my model predict. And then I can understand what larger scale environmental variable control them using equation discovery that simply combines my variables, apply some functions that I ask the model to use or allow the model to use, and it comes up with an expression that best explains those data. Okay, thank you so much, and I look forward to your comments.
Thank you so much, Sarah. Any questions?
Can you say a little bit more about how the first step of estimating these conditional joint distributions goes into the equation discovery? Because I didn't quite catch that.
So thank you for the question. So if I have, let's say, this model that is trained and it's doing pretty good, for each larger scale variable, like here my XL, you can think of it as a combination of moisture and temperature, for example. I can sample from my noise, and I pass different noise combined with that larger scale. That's going to reproduce this distribution. And then I compute the statistics of that distribution, its mean and its standard deviation. So now I have a pair of mean and standard deviation with a larger scale condition. And if I iterate over all of my larger scale condition, then I have those pairs for all of the larger scale condition that I had. Then I use those means and a standard deviation as the target to my equation discovery, and those X of L's as the input to my equation discovery. Sorry, there was so much detail missing there. Thank you for asking.
What kind of machine learning tools is being used in this study? And like equation discovery for that, you have used like some algorithm like Cindy or something, or like how that is being calculated? And nice presentation, by the way.
Thank you. Could you repeat the question?
Oh, what kind of algorithm you have used in the ML
Oh,
tool? And you
yeah.
talked about the equation discovery. For that, you have used like sparse algorithms like Cindy, or how's the equation discovery is being calculated?
Yeah, so the environmental variable that I use, I average them over free troposphere and boundary layer. So for each of them, I have only two variables, right? And I'm using precipitable water, relative humidity, temperature, velocity, CAPE, equivalent potential temperature. So that gives me 2, 4, 6, 8, about 10 variables plus surface temperature. And then the algorithm that I use is called PySR. It's based on it's based on genetic algorithm. I can define a library of function that I allow the model to use, and also a list of inputs. It's gonna combine the inputs, apply the functions, and try to come up with an equation that best describes the outputs.
Okay, thank you.
Thank you.
Great. Any other questions on Zoom? You can feel free to unmute yourself.
Hi, Sarah. Thanks for the presentation. I wanted to
Diane.
ask, hi, I wanted to ask in PySR, do you just use like the basic for operators, or do you use something more than that? So is it just polynomial, or is there like exponential, something else as well?
I did add few more. So I have I think I have a logarithm function. I have exponentials. I have, what else I have? I think I have a ReLU to get rid of the negatives. I think that's it. I don't have a large function library. So yeah.
Sorry, could you show your results from the ED again? That slide.
This one?
Yeah.
Yep. So this G and F, those are two linear functions of W's, of omegas. Sorry, it's like a constant value minus omega. I wanted to feed it in the same slide, so I didn't write it down.
I see. Am I right in saying though that all the extra functions that you added in didn't seem to appear in the end? Am I saying that right?
Yeah, that's true. So in this case, they didn't appear. That's a good news. Although, like the model outputs 20 equations and I have to pick my favorite, so I pick the one that stays between accuracy and simplicity. If I go to more complex equations, they have a better prediction, but they are not nice to look at. So those more complex equations, they sometimes include logarithm or exponentials.
Yeah, sure. Thank you. I think it was just interesting to me that often when using PySR, the things which are not polynomial end up falling out. But
Oh,
yeah, so
yeah.
that is just something I was looking at. Thank you.
Thank you.
Could you say a little more about the relationship, like how physically, compared to other studies, how physically realistic are to what extent do you like these equations essentially? Do they make sense based on, understanding of how this actually works physically?
I like them a lot. So most of the works that have been done on precipitation is directly on precipitation itself, but not the precipitation area. If I compare them, like if I compare these equations with what people expect to get when they talk about precipitation, then the variables that pops up, it's pretty reasonable. So the power 3, I cannot explain it yet, but this power 1 here, that's pretty reasonable. So there are a few versions of it. So some of them, they use equivalent potential temperature. So that's a measure of, let's say, a mixture of temperature and humidity. If I use that variable, my model subtract the temperature out of it and leave it as a moisture variable, and it only uses that, which is heartwarming. It tells me that, okay, maybe this PW is a better variable. But there is also an argument whether we should use boundary layer versus free troposphere to explain precipitation, whether we should use relative humidity, precipitable water, or equivalent potential temperature. And my model kind of like constantly picks up these variables. So that is a nice result. Another thing is that this omega 500 is not a popular variable because models are not accurately predicting it. So if I use it in my model, and then if I implement that as a parameterization, my parameterization has a chance to go wrong. So I have versions of this that I replace that omega, or I remove that omega out of my data completely. The R squared drops to 0.7, which is not bad, but then I have to accept that I have a more complicated equation. Yeah. Okay.
Thanks for the talk, sir,
Thank you.
and all the great questions. Thank you so much.